Starting. Okay, so today is our second session in Module 4. The last time we were together, if we look at our learning plan, um, we got through the first part of our PowerPoint presentation. So today we're going to continue on. We're actually going to revisit our handout first, and then we're going to be finishing up or looking at the second PowerPoint presentation that we have here. And that most specifically is going to be on what we call the relative velocity method to solve for velocities in members of a mechanism. So we've already gotten through almost halfway in the Chapter 6 velocity handout that we have here. If you were here last time in the room, I had the copies made. If you were virtual, then you had to print out those copies. And this is going to be part of what you're going to be handing in for the practice problem. So what I'm going to do is I'm going to go underneath our camera here, and the page that we're ready to get started on here in the handout is page 5, okay? So what I want to do is, this is kind of things to remember from the last time we were together, to kind of recall equations and units and all that kind of stuff for some specific things. So first of all, in the beginning of Chapter 6 here, or Module 4, we learned about the relationship between straight line velocity and angular velocity. And we saw that when we have members that rotate, they have angular velocity, but points along that member also have straight line velocity. And we can, calculate both of them based on the information, that we have about a problem. So when we're looking at straight line velocity, there are two equations that we would keep in mind. The first one is kind of our familiar standard straight line rectilinear velocity equation, and that's going to be V is equal to d over t. So to calculate the magnitude, if you would, of a velocity, we would use V as our variable, and then we're going to take whatever distance we cover divided by the amount of time that it takes to get there. Now, sometimes we see this, and we saw it in a couple different forms. Sometimes we see that distance with the variable s, and in the book, they had it as a variable capital R. Okay, so all of these are distances. And then time was consistent as far as the lowercase t. So velocity is equal to distance divided by time. Okay, now we also saw a rearrangement of our angular velocity equation where we could say, oh, velocity can also be calculated if we know how, or straight line velocity can also be calculated knowing how fast an object is rotating about a fixed center. So that's going to be our W, our angular velocity, times how far that point is away from its center of rotation, or its radius away from the center of rotation. Okay, so we could say where V is equal to velocity, okay, D, S, and R are equal to whatever distance we're dealing with. T is equal to the amount of time, right? As we kind of look at the variables that we have here. Our W is angular velocity, okay? And that R is going to be the radius. And that's when these two are when we have rotational motion, how fast it's going around a fixed center. And then this is how far it's away from that fixed center. So radius is an appropriate variable, if you would, for distance away from a center of rotation. Okay. Now, units for straight line velocity. What are we expecting for units, final units for straight line velocity? Nope, not just inches. Remember velocity. If we're going to take distance divided by time, what would the units, what would be an appropriate set of units for straight line velocity? Yeah, feet per minute would be good ones. So feet per minute. What else? If you're virtual, feel free to put it in the chat box if you want to. So feet per minute. What else? What other units will we see? Inches per second. Yep, got it. Inches per second. Excellent. Miles per hour. Yep. Miles per hour. So anything where we have, not revolutions per minute for straight line velocity. That's going to come, Joseph, for angular velocity. We'll hold tight on that one. But anywhere where we're covering a distance, a straight line distance, and and it's within a time frame. Okay. And in this case, we would say when it's per minute, per second, per hour, we would call that a rate. Okay. Like an average amount of distance we would cover in an amount of time. Okay. Now, direction to fully define, because we know that straight line velocity v is a vector quantity. So we have to have both magnitude that we're going to calculate using an equation, and then we need to determine what its direction is going to be. So for the direction of straight line velocity, it's always going to be perpendicular. So I'm going to use this symbol of perpendicular to the radius of rotation, comma, in the direction of the rotation. So DIR is direction of rotation. Okay. Now this goes back to the illustration on the very first page that we have. Okay. So when we have, for instance, a link that is rotating around a fixed center, so in this case, it's going in a clockwise direction, a velocity of any one of these points, X, Y, or Z, you're going to notice that a straight line velocity vector is drawn here. It's drawn perpendicular to the radius back to its center of rotation. And it's pointing, in this case, down and to the right because it is in the direction of rotation. Does that make sense? So the direction of the straight line velocity, perpendicular to its radius back to its center of rotation, and it's going to be in the direction of that rotation. Okay. So we would not point this up and to the left when it's rotating clockwise. Okay. All right. So direction of straight line velocity, we always can kind of know. So it's perpendicular to that radius of rotation and it's in the direction of the rotation. So let's look at angular velocity. Angular velocity, to calculate it, we're actually just going to rearrange this for W. Okay, so our variable for angular velocity or rotational speed or rotational velocity is going to be W is going to be equal to V over R. Okay, V over R. Now, Joseph, here are our units. Units here for angular velocity are going to be RPMs or revolutions. I like how you wrote it, revolutions per minute. Okay, RPMs. The other units that we found out about, and because in this equation, we'll say, I like to say in and out of this equation, we also know that we see radians per second. Okay, those are the two units that we're going to be using for angular velocity. And that is consistent in both English units and in metric units. Up here, straight line velocity, it's going to depend. If we're in English units, it's going to be this feet, inches, miles, right? If it's metric, it's going to be millimeters, centimeters, meters, kilometers, okay, per whatever unit of time. But down here, the units remain RPMs, which is universal, and radians per second. So that's going to be universal as well. As far as direction of angular velocity, and again, angular velocity is when we're rotating about a fixed center and we represent it with our W, okay? And the sub 2 here is link number 2. It's really going to be, is it clockwise or counterclockwise? Which direction is it rotating? So it's really one of two directions. So it's going to be clockwise or counterclockwise, okay? So questions on here at all or comments? All right. So let's turn the page. And before we move on to kind of the new subject for today, we have two little examples here that kind of review some of the information we had last time. So for instance, it says, draw in the velocities. Okay, so this is going to be our V, okay, our straight line velocity on each one of the links. So if we look here and this is supposed to be for point B. If we look for point B, it's at the end of each one of these links. So if we look at the first example on the left-hand side, you're going to notice that we have the angular velocity W is going in a clockwise direction here, okay? So if we look at where B is, you're going to notice it's on the end of this link. So the direction or drawing in that velocity, we're going to draw it perpendicular to our link, okay? So perpendicular, and we're going to draw it going down and to the right, and then we're going to label it VB, okay? Notice that it's consistent with the direction of rotation, right? So if I would put my finger on A and pull in the direction of velocity of B, it would be consistent with the rotation of that link. And it's also going to be perpendicular to that radius of rotation back to point A. So what you want to do is you want to add the VB for each one of the illustrations here. So I'll give you a little bit of time to do that, and then we'll compare in just a second. So add your VBs to the next two. I'm going to add them. So you should see the middle one, VB, going up and to the right. Its angular velocity is going in a counterclockwise direction. So if I put my finger on A and I pull in the direction of my velocity of B, it is consistent with the direction that this is going to rotate, right? And if we look at the last one, we're going to see VB going, if you would, horizontal to the left based on the orientation of our link. And again, if I pull in the direction of my VB, it is going to be consistent with a clockwise direction rotation of that link where W is going clockwise. Any questions on these three in the direction of VB? Okay. Then let's draw the correct direction of the angular velocities here. So angular velocities are going to be our W's, right? And in this case, we're given the velocity of B in each case. So go ahead and draw your W's with your arc, showing it going clockwise or counterclockwise for each one of these cases. And I'll put mine here too. So for the second one, you should go clockwise. And for the third one, you should see it going or have it going counterclockwise. Any questions on those three? Okay. All right.
Is that W?
No, this is just so the question was, is that WA? No, remember, point A is not moving. It's considered a fixed position. It would be W of whatever the link number would be. Okay, so most often, if this is kind of, if you would, the input, we would probably call our frame 1, right? Or we would call our frame 1, and then this would be 2, so then this would be W2. Yeah, we'll see that. We'll see that when we start applying and putting our link notification or our link and joint callouts and labels on. Yeah, good. Any other questions? All right, then we're ready to turn the page and start looking at a new subject. Okay, a new subject. Now, what I'm going to do is I'm going to kind of start us out back under Module 4, and I'm going to open up the PowerPoint presentation, part 2. Okay, so this is still chapter 6. We're going to continue on, but now we're going to be looking at section 6.6, which starts on page 130. 130. And we're going to be looking at what we call a relative velocity method, but we're going to be using the graphical version of that. Okay. So relative velocity is when we need to determine what the velocity is of an element or a link in a mechanism that is dependent on the velocity of another link. Okay. So if we look at, I'm going to go back underneath here. If we look at on page 7 in our handout, we have just a common 4-bar mechanism. So we've seen these, we've drawn these many times in our previous modules. So you'll notice here at A and D, these two links are attached to the frame. Okay, we have the symbol for the frame and we have it called number 1. Okay. Then what we have is you're going to notice that we have link number 2 identified, and in parentheses here, it says that it's the crank. So what that would mean is this is probably where we have, I'm going to call it the input motion. Sometimes it might be driven by a motor, might be driven manually by a crank, whatever it might be. Okay. But this is where we're getting input. And you're going to notice that we are showing an angular velocity of link number 2 here. Okay, so this is going to be going around in a clockwise direction. So right here, we would say this is, by all indications, what we would have as our input motion. Okay, link number 2 is going to be our input. Now, link number 2, we're probably going to know everything about it because many times we do know, oh, the crank is rotating at 1100 RPMs, okay? And a very common problem that we want to know is, well, how fast is number 4 moving, okay? We can't say it's going to be going at the same rate as the input link because many times these distances, the lengths of links number 3 and number 4 are then going to probably not be the same as link number 2. Most often they're not in almost all of the, actually probably all of the illustrations we looked at. And by adjusting those, now all of a sudden we can figure out, okay, what is going on over here? So we would want to know what is a very common problem is, what is the angular velocity of link number 4 when link number 2 is rotating at blah, blah, blah RPMs, okay, or identified number of RPMs. Now, this mechanism, we would know everything about it. We would know how long each one of those links are. We would know at what position it is. We would know what's going on in the input. So then we could figure out what this is. And we're going to figure out what the angular velocity is of link number 4 relative to what's going on link number 3 and link number 2. So we call it the relative velocity method because this motion is relative to what's going on over here. Okay. We sometimes refer to these links 3 and 4 as slave links. Okay. Our input is here, or the master truly is what we call it. And then the slaves, they're dependent, they're relative to what's going on over here. It's not meant to be anything bad. It's just kind of how it kind of works out. Okay. All right. Now, the relationship of calculating straight line velocities is still going to hold. So we had learned that the velocity, straight line velocity of a point on a link is going to be equal to the angular velocity of the link that it's on times how far it is away from its center of rotation. That's what we see here. So if we look at link number 2 and we want to determine what is the straight line velocity of B, it's going to be dependent on, or it's going to be calculated using the angular velocity of link number 2, W2, and how far away from that center of rotation it is. Okay. All right. Now, that straight line velocity of a point on link number 1 where we know the stuff over here on the input, we now can figure out, okay, what is the velocity then going to be at link number 3? We don't know what that is. That's considered what we call unknown. Okay, but we do know it's going to be relative to what's going on over here at B and what's going on this link right here. Okay, we're going to find that out. So if I go back over here, sorry, this one, we are going to be able to find out the velocities of different points on those links in that 4-bar mechanism by using the vector equation we see right here. Okay. So it's the velocity of an unknown variable. Okay, this is going to be the one we want to solve for. So for instance, in our case, it might be the velocity at C. Okay, that's going to be our unknown variable, assuming we know everything about over here. We're just kind of using this as a scenario or the process we're going to go through. Is going to be equal to the velocity of the known quantity. Okay, so the known quantity is going to be on our input most often, or it's going to give us the most information. So we would know, and we could calculate the velocity most often at B here. That would be a known variable. And then the third vector is going to be plus vectorially the velocity of the unknown relative to the known. So the velocity of, if you would, a point on a link that connects those two points, known and unknown. So it's going to be what we call C relative to B here. Okay, so this is the vector equation we're going to use, and we're going to continue to apply in different ways on different 4-bar mechanisms. Okay, the two main types of 4-bar mechanisms are going to be like what we see here. This is going to be a crank and an oscillator at the end. So this crank is going to go around, and this is going to oscillate back and forth. Okay, the other type of mechanism that we've seen a lot of is a slider crank mechanism. Okay, these are the two that we're going to be analyzing through the examples we do here at the end of this second part of this lecture, as well as the homework that you're going to be doing. Okay, the homework that you're going to be doing. Now let's kind of go back here, kind of fill in or talk about the items that are here. So this is our base relative velocity equation, okay, for the illustration that we see above. So assuming we know everything on the crank, how fast it's going, how long it is, that the velocity of B here is out here, we can draw the velocity of B in place. Go ahead and do that. Draw me the vector VB at the end of link number 2. Now we've been seeing previous to this page, all of our links have been just one link, right? So at the end point there, this really doesn't change. Just show the velocity of point B on the end of link number 2 as you would draw it based on the information you have here. We don't have numbers. We can draw the vector. Now, we know that straight line velocity, VB, is going to be perpendicular to its radius back to its center of rotation. So right here, we know that VB can only go on a circular path that has a fixed center at A, right? Okay, so the velocity at B is going to be perpendicular to that radius back to its center of rotation. So it's going to be 90 degrees, and it's going to be in the direction of rotation. So velocity B is right there, going down and to the right, correct? Okay, makes sense? So that is one of the variables in our problem here. Okay, so velocity of C, straight line velocity of C. Velocity of C is at the end point of link number 4, which also rotates about a fixed center, in this case D. So it can only go along that circular path, right? Now, if we look and we rotate link number 2 in the direction, in a clockwise direction, and if we kind of envision what this is going to look like, we'd have to move things around, but chances are this is going to start moving in a clockwise direction as well. Would you agree? Okay. So we're going to show the velocity of link or of point C to be up and to the right, perpendicular to its radius 4, or the radius or the distance back to its center of rotation. And this is going to be velocity c. Okay, that's going to be one that we're going to want to find. That's going to be considered an unknown. Okay. Now, the other vector we have here in this equation is c relative to b, or unknown relative to the known. So you could have different variables here at times, but we're going to see these kind of come up over and over because we're going to be dealing with our three bar mechanisms, and we're going to be lettering them and labeling them, you know, how we've been doing up until this point in the class. So this will kind of be a very common variables that we'll be using. But c relative to b, or unknown relative to known, this is going to be the straight line velocity of the connecting link. And how we draw that in place is that this one is simply going to be, and I always draw it as a dashed line because I don't know, and I put the arrowheads on either end, I don't know if it is going to be going up or if it's going to be going down. Okay, but I do know it's going to be perpendicular to the line or the link connecting the 2 points that we're dealing with here. And this is going to be the straight line velocity of c relative to b. So it would be c/b. Okay. Don't worry, we'll get a lot of practice on this. So if you're like, I don't understand how she knew where that stuff was, we'll have examples with numbers and we'll go through this again. Okay. So we drew in place VB, VC, and C and B relative. I'm sorry, this should be C relative to B, not that's got that mixed up. C relative to B. It is important that we have it in the right order. You might be like, does it really matter? It does. It's always unknown relative to known. And in this case, our unknown is C, assuming we know everything about the crank, the input, and C would be considered an output. Okay. Now, it says here, draw in W4 too, or also. So W4 is going to be the angular velocity of link number 4. Link number 4, we drew the VC, right? Straight line velocity of the point on the end of that link. We have it going up and to the right. So that would mean that our angular velocity of link number 4, as long as that's confirmed, that direction would be going in a clockwise direction. Okay. So make sure you're filling in all of these items because this will be a good reference back when you're doing your homework of just kind of the directions on how things are related. Okay. So questions here. Questions here. When you hand this in, I'll be looking to make sure you do have these things, you know, added. All right, let's turn the page. And let's kind of do this very same thing, but this time we're going to do it for a slider crank mechanism. Okay. The other one was like crank or crank oscillating. This one, our output is going to be going back and forth horizontally. In this case, it's a slider. And then our input is going to be a crank going all the way around. So this is considered another relative velocity problem because if we look at our slider's velocity, straight line velocity, is going to be determined or relative to what's going on over here. Again, link number 2, this would be our input. This would be dictating and putting motion into this mechanism. Okay. Now we're going to use the same vector equation. The velocity of C is going to be equal to the velocity of B plus vectorially C relative to B. Now, just like our last problem, okay, we're going to start over here on the input and point B is here. Draw in for me what you think the direction of the velocity of B would be. Hopefully you drew it going up and to the right, perpendicular to link number 2, because that's the straight line radius back to its center of rotation, because it's only going to go along a circular path in the direction of rotation. Okay. Now, again, many times on that input, we know how fast it's going. So a lot of times we'll say that's where we know the most information. So this is probably going to be a known quantity, velocity of v. So that's in the known quantity area. The unknown quantity, velocity of point C. Velocity of point C is on a slider. Okay, so this slider's motion is not going to be about a fixed center, but instead it's going to be along a horizontal line going through point C. I didn't get it through point C. Let's put it through point C. It's going to be along this line, right? Right? It's going to be constrained, if you would, to only horizontal straight line motion. So as I rotate clockwise from this position, do you see how the velocity of C is going to be horizontal and to the right? It's going to pull to the right, right? Does that make sense? Okay. But notice that its magnitude is going to be dependent on how fast this is going around. If this is going kind of slow, let's say 100 RPMs, not going to move super fast to the right. But if it's going, let's say 1700 RPMs, that's probably going to go pretty fast to the right. Okay. So its velocity is going to be relative or dependent on our input link or on how fast link number 2 is rotating. Okay. So that's why we say it's relative velocity. Okay. So unknown velocity is equal to the known plus the velocity of the known relative to the, the unknown relative to the known. This again, the direction of the velocity of C relative to B is going to be perpendicular to the line connecting or the link connecting B and C. So we would, and again, I always put it dashed just because we don't know how long it is and we don't know its direction, but we would call this the velocity of C relative to B. And again, perpendicular to the link or the line connecting the 2 points that we're dealing with here. B being the known, C being the unknown. Okay. So here on this one, we only have one angular velocity, and that's going to be on our input. And we have straight line velocity on our output. So there wouldn't be a W4 in this case. There would just be a velocity of point C. Okay. So as we look here, the direction of the velocity of the slider is along that line of action. Draw the vectors on the diagram, which we did. Okay, so make sure you have those added. Again, these will be nice references for you when we're doing the example problems. Okay. All right, let's go back to our PowerPoint presentation to kind of catch us up. All right, we will be applying the W is equal to V divided by R. Points on links limited to pure rotation or pure translation. So pure rotation are going to be the ones that are only moving along a curved path that have a fixed center, okay? So first of all, when we kind of go through this process, we have to determine the rotation of whatever the unknown velocity is. So in that first illustration that we looked at on page 7 in our handout, over here, oh, hit the wrong button, this one. We would want to kind of determine our unknown velocity or output here, our angular velocity. We would kind of be like, okay, if W2 is going to the right, what direction would link number 4 be going? And it's probably going to also be going to the right or in a clockwise direction. You just want to kind of visualize that to start out with, okay? Then the second part is here, determine the direction of the relative velocities between the two joints. So that means when we go back over here, the relative velocity is going to be this C relative to B, okay? And it is going to be perpendicular to the link connecting your known and your unknown variables. So we saw it here perpendicular to link number 3, and we also saw it on the slider crank mechanism, also link number 3, connecting that B and C, perpendicular to. I always like to say, if you're ever, unsure of a direction for a straight line velocity, it's always going to be perpendicular to something, okay? So Velocity of B is perpendicular. Velocity of C relative to B is perpendicular. Okay. Use the relative velocity equation to draw. What we're going to find out is going to be a vector polygon, or it ends up being a triangle because we're just dealing with three variables here. So the velocity of the unknown is going to be equal to the velocity of the known plus vectorially unknown relative to known. Make more sense when we do some examples here. And then through that graphical means, we're going to find intersections. We're gonna dimension to find and determine what the unknown magnitudes are for any vectors we're trying to find. Okay, so let's go to page 7 in our velocity handout and look at our first problem to kind of make sense of the stuff we've been talking about here and put it into an application context. So we are going to open up our books to page 162. And we are going to do problem number 620. 620 is right here. So on page 162 in the second column, okay, we are going to work with the compressor linkage that we see right here, okay? And I'm going to erase the notes I have because I don't know if those are consistent with this problem, okay? We're going to work with this linkage. So we're given, where it's sitting at this time in space, okay? So for 620, it says here, for the compressor linkage shown, use the relative velocity method to graphically determine the linear velocity of the piston. So the piston's over here as the crank rotates counterclockwise this way around, okay, at 1775 RPM, okay, 1775 RPM. So let's go underneath here. And in our handout, it's giving us kind of the process that we're going to go through. So let's look at the process first. First thing we're going to do is we're going to draw our kinematic diagram, okay? And we're going to do that in CAD. So we're going to take time to go over to AutoCAD and we're going to draw it to scale as we see it, okay? So it's going to look like this. We've got a slider going back and forth. That's going to represent our piston in line with the center of the crank that's going counterclockwise at 1750 RPM. We're going to add all of our labels for our links and our joints, okay? Then the next step is we're going to, and I'm going to kind of go down here first. We're going to use that relative velocity equation to find out what is the velocity of our piston. And our piston is going to be this slider, okay? So we're going to use that relative velocity equation. So the velocity of C, because that's going to be the center of our piston, is going to be equal to velocity of B. We're going to be able to calculate its magnitude and we're going to know its direction. That's going to be a known quantity, plus vectorially the velocity of C relative to B, okay? And using the information from the previous page, really this one, because this is a slider, we're going to use these directions and such and apply them to our application, okay? Now, once we determine those velocities, then we're going to have a final answer, okay? We'll kind of see how that develops. So for this problem, the first place we're going to start is draw the kinematic diagram. So we're going to go over to AutoCAD, and I already opened up my kinematic diagram here. For this problem, the units are English. So if you want to open up your kinematic start file, go ahead. And what you're going to do is you are going to draw the kinematic diagram. I'm going to give you a couple minutes to do that. I'm going to pause our recording and then I'll be back once we kind of have everything in place. So I added just a couple dimensions here just to double check the geometry. It's really important that we have everything at the right angle, at the right size. Otherwise, as we are creating our vector diagram, because we're going to use the geometry to help us with directions, things won't come out. Okay, so it's really important. So I added these dimensions. I'm going to delete them now just for the purpose of checking my dimensions. Okay, so once I have my kinematic diagram in place, I am ready to kind of, use my relative velocity equation to help me with some items here. So let's go back underneath. Now that we have this all set up in AutoCAD, we're going to be using this relative velocity equation. okay, this relative velocity equation. Now, each one of these variables here is a vector, okay? And each one of our vectors, oh, hold on. Do we have to extend the base of the slider? I'm not sure what you mean by that, Garrett. Do we have to extend the base of the slider? You mean like to meet up? You made it really wide. That's just how mine was. I mean, it just has to extend beyond. You mean like this part right here? Yeah. It's a random length. Yeah. Okay. So each one of these quantities here needs both magnitude and direction to be fully defined. Okay. So what I do for each one of mine is what I'll do is I'll identify, do I know the magnitude? Do I know the direction? So you'll notice here that we have velocity of c. Velocity of c is our, I'm going to put un, our unknown quantity. Okay. So that's going to be the velocity of c. The velocity of c is going to be how fast this piston is going back and forth. That's what the problem wants to know. And the first variable is always the unknown quantity. Okay. We also see this back when we were on the beginning of this section. The base equation is the unknown velocity is going to be equal to the known. So our unknown velocity is, what is the velocity of our piston? Okay. Now, if I draw it in here, and I know it's a slider, it's going to go along a horizontal line here, right? And we know that based on the description or the problem statement is that the crank, link number 2, is going to be rotating counterclockwise. So at this instant in time, if this rotates counterclockwise, do you see how that is going to push the velocity c to the left? Would you agree? Okay. And it's going to be along that horizontal line. So we know its direction. Agreed? We know its direction. We just don't know its magnitude, right? So if we look down here, what I'm going to do is I always have like each one of these has, if you would, 2 items we have to define. I'm going to put a circle because we don't know magnitude for this vector, but I'm going to put a check for knowing the direction. Okay, so magnitude, direction. So I don't know magnitude for velocity c, which is the velocity of, whoopsie, I froze up here. The velocity of our piston, okay? But I do know its direction, not the magnitude. Now I'm going to cross the equal sign. I'm going to look at vector b. So the velocity of b. B is at the endpoint of link number 2, which we know rotates in a counterclockwise direction at 1775 RPMs. I can draw vector B to be perpendicular to link number 2, pointing down and to the left and in the direction of rotation. Do you see that? Okay. So its straight line component of point B, the velocity of point B, is going to be down and to the left. Okay. Now, I know direction of B, right? So down here, kind of on the right, magnitude, direction, I know direction. Okay. But do I know magnitude? I might not know it right now, but can I calculate magnitude? I sure can. I can calculate it using our equation. Straight line velocity is equal to angular velocity times the distance of that point away from its center of rotation. So we can say the magnitude of the velocity of B is going to be equal to the angular velocity of link number 2 because B is on link number 2. It's on the endpoint of link number 2. And how far away? What is its radius? Okay, so when we look here, we know what W2 is, right? We know it's 1775 RPMs. We know R2. We know the distance from the center of rotation out to B, and that was 2 inches, right, from our problem. Okay, so we know these 2 quantities. We can calculate the magnitude of the velocity of B. Go ahead and do that. Go ahead and do that. Before you do, make sure you put your W2 into radians per second. Don't use 1775. You should get something very close to 371.74 inches per second for the magnitude of the velocity of B. Okay. So again, link number 2 is our input. We know that it is going to be inputting a motion of an angular velocity of 1775 RPMs going counterclockwise, of which B is on the end of, okay? And it is 2 inches away from that center of rotation, so we can calculate its magnitude. So that means when we go down here, this is, if you would, the magnitude of the velocity of B. So we can say we have B fully defined. We know both its magnitude and we know its direction, right? We do. We do. So this is 2 of the 3 vectors of our vector equation. The third vector is going to be the velocity of C relative to B, or unknown relative to the known. All right. So as we stated earlier, the velocity of C relative to B is going to be perpendicular to the link or the line connecting those 2 points. Okay. So that means that direction-wise, that velocity, I don't know if it's going to go up and to the left or down and to the right, is going to be the velocity of C relative to B right there. And it's going to be perpendicular to link number 3. Okay. Now, we don't know what the angular velocity is of that link. We don't know. We do know how long it is, but magnitude-wise, we don't know what C relative to B is. But we do know direction. We do know that it's perpendicular to the line connecting those 2, okay? All right. So now, as we look at our vector equation, we've got 2 unknowns. two unknown magnitudes. We've got the magnitude of the velocity of c, and we've got the magnitude of the velocity of c relative to b. That's two unknowns in an equation. Is that a problem for us? Is it? It's a vector equation. It's not a problem. Remember when we did our vector equations in our previous module, we could have two unknowns as long as there was only one on one side of the equal sign and one on the other. And we do have that. So we're not afraid of this. This works out. This works out for us. We can have no more than two unknowns in a vector equation, and they have to be separated by the equal sign. Okay, and ours are. So this works out well for us. So what we're going to do now is we're going to find the magnitude of VC and C relative to B using a graphical vector equation. Okay, so let's go ahead and go back to AutoCAD. Okay, now I'm going to kind of go back and forth underneath our thing here. So what we're going to use is we're going to use AutoCAD to help us to create and get the directions for each one of our vectors. Okay, so I'm going to go kind of back and forth underneath here. We're going to start our equation where we know the most. So as we look at our vector equation, what do we know the most about here? Which variable? Which has the two check marks? Velocity of B, right. And you'll notice that it's the first variable after our equal sign. So our equal sign, as we know, is our origin. So we're going to draw an origin, and the first vector we're going to put in place is going to be the velocity of B. So let's go over to AutoCAD. Now, our magnitudes here, the magnitude of B was 371.74, and the length of our link here was 2 inches, okay? If we draw a vector that is 371 units long at this point, it's going to be huge compared to our diagram. So we're going to scale it, okay? And so we're going to scale it by dividing our number here by 100. So we're going to draw the length of our vectors 1/100th of what they are. When we report the values in their final form, we're just going to have to multiply them by 100. Does that make sense to everybody? So the length of vector B is going to be 3.7174. Okay. All right. Now, we also know that B is perpendicular to link number 2. Well, I already drew link number 2 in place here. So what I'm going to do is I am going to draw a line, and I'm going to go on my object 2 layer. I just want it as a different color, okay? If you need to create a layer with a different color, that's totally fine. And I'm going to draw a line, and I'm going to just go random distance out here, all right? I'm not too concerned about the length right now, so I'm going to left click. And then what I'm going to do is I am going to draw this line perpendicular to link number 2. So I'm going to do shift right mouse button, and I'm going to find where perpendicular is, and I'm going to select link number 2. Oops, it went to my label, my circle. Let me do that again. So line out here, and shift right mouse button, perpendicular. Make sure you grab the link, okay? Just a random. All I've got now is direction, okay? What I'm going to do is I'm going to move the endpoints here to the endpoint of where B is, because this vector is going to be at point B, okay? And then I'm going to draw a circle center radius. So I'm going to go from the endpoint here where B is, and tell me what my radius is going to be. I want to make this vector the correct length. What is going to be the radius here? Nope. I want it to be as long as the magnitude of velocity B. So how long is my radius going to be here? If I make it 371, it's going to be really big. What did we say we were going to do? Not 371. We're going to make our radius, Joseph said 3.71. Yes, so that it's more proportional to our length here. And then we're going to have to just report out our final answer to be multiplied by 100. So 3.7174. Okay, is my radius. So now what I'm going to do is I am going to trim off the end that goes past my radius. If your vector or your line wasn't long enough for your radius, then you're going to do the extend function. If it went past, you're going to do the trim function because I want it to be the exact length it needs to be. Now I'm going to erase this, okay? And then I'm going to add my vectors just like we did before, my arrowheads. So very simple, crude arrowheads going down and to the left, right? Because my W2, I don't see it on here. That's okay. My W2 is going in a counterclockwise direction. It's rotating this way. Now I want to label this vector as well. So I'm going to copy my B and I'm going to label this VB. Okay. So velocity of V. So I've got it at the correct direction and I've got it at the correct magnitude, the correct length. Okay. Any questions about that? Now, having these here is going to be part of what you're going to hand in. You're going to be showing your diagram with the vectors in place, okay? Now, the next vector I'm going to draw here is going to be vector C relative to B. Now, as we drew it up here, we sketched it. It was perpendicular to link number 3, but we didn't know, how long it was going to be, and that's okay. So we're just going to go back to AutoCAD. I'm going to change my layer to object 3. I'm going to draw a line, random from out here, but perpendicular to link number 3. Okay, I'm not even going to put an arrowhead on it because I don't know if it's going up and to the left or down and to the right. All I know is direction. And then I'm going to label this the velocity of C relative to B. Okay, make sure it's C first / B. Okay. And then the last one I need to add, I'm going to change to my object 4, which is just another color, is going to be the velocity of C. If I go back underneath here, remember C is a piston. Now, although I put an arrowhead here, we're pretty sure it's going to go to the right. We don't know its magnitude, though. So we just know, if you would, line of action is going to be horizontal. So if I go back over here, and I'm just going to draw a horizontal line, and whether it's going to the left or to the right really doesn't matter. And I'm just going to draw it a random length, and I am going to label that the velocity of C. Okay, that represents, so no arrowhead on that. So this is going to be one of the screenshots that you hand in. This is going to be your kinematic diagram of your mechanism with all the labels, as well as any information we know about the 3 vectors that are in our relative velocity vector equation. Okay? Any questions right now? All right, now we want to do our vector equation. So we're going to use our vector equation right here. Now, first of all, I'm going to write our vector equation out. So I'm starting with the velocity of C, and I'm going to put it over here on the right. Okay, double click, make this longer. This is going to be the velocity of C is going to be equal to the velocity of B plus vectorially, so make sure you use the greater than sign, the velocity of C relative to B. Okay, that's our vector equation. I'm going to go back to my object layer. Just going to kind of figure out here, go down. So I'm going to put my origin right about here. Make sure you identify an origin. Okay. Because this is going to be our equal sign. Now, as we said earlier, the vector we know the most about is the velocity of B. We know how long it is and we know its direction. So we are going to copy, do not move, you're going to copy vector velocity or the velocity vector B, and you're going to put its tail at the origin. Okay? Right there. So make sure you leave a copy behind on the diagram. Don't move it. You want to copy it over to the origin because I want to see this that you use the diagram to put these in the correct orientation. Okay? And now on the end of, I'm going to add the velocity of C relative to B. So I'm going to do a copy again of C relative to B, and somewhere kind of along the length of that vector, I'm going to then at the endpoint place C relative to B. Okay. I don't know if it's going to go down and to the left or I'm sorry, up and to the left or down and to the right. So I'm just going to kind of place it right there on the endpoint, okay, on the tip of velocity of B. All right, now I've exhausted everything on the right-hand side of the equation. I'm going to cross over the equal sign, which means I go back to my origin. And now what I'm going to do is I'm going to place my vector velocity C. So I'm going to copy velocity of C. And I'm going to grab the endpoint, and then I'm going to put it at the endpoint or at the origin. And my velocity of C is going to be here. Okay. Now what I need to do is find my intersection, right, for my unknown values. So all I'm going to do is I'm going to extend my velocity of C relative to B, and then I'm going to trim off anything that extends beyond those, okay? So I've got a triangle. Now, I need to add my arrowheads for these vectors. So I'm going to use my vector equation to determine where my arrowheads are. So I know I'm going to start with VB. I'm going to take VB plus C relative to B. So that means I'm going to add these tip to tail. So I'm going to go back to my object 3 line. That means my arrowhead is going to be here. Okay. So the tail of C relative to B is going to be on the tip of B, and then its arrowhead is going to be up and to the left. Everybody understand that? Does that make sense? So then I have everything defined on my right-hand side. I'm going to cross over the equal sign. And for the velocity of C, the tail is going to start at the origin, and the tip is going to go to the tip of the last vector on the right-hand side of the equation. So that means that my vector is going to point for VC to the left, which is what we were anticipating, right? Okay. So do you see how we use the relative velocity equation to now solve for not only the magnitude, but also the direction of the two unknown variables. Okay. Is the yellow line? Is the yellow line found the opposite way in both graphs? I guess I'm not sure what you're asking. I don't have a direction here. I'm thinking you're wondering, is it going left from the origin? Yes, yes. Now, this is only a direction, Aiden. It's just that it's a horizontal line. It can, you could extend it. I just had D in the way. Oopsie. I had D in the way. You could extend it. It would go either way here. Does that make sense? It was not intended to say, oh, I'm going to the left or right. It's just a line of action. That's it. And I had D on the other side there, and I didn't want to go through it. Okay. Now, does it make sense? But after doing the vectors, now we know it goes left. Yeah. Yeah. It's like confirmed. Correct. And if we double check, this is rotating in a counterclockwise direction. So it's going to push that slider to the left, right? So we're expecting it to go to the left, and it's confirmed by this direction here as well, by the arrowhead. So now we have the directions identified. How do we get the magnitude? We need to find the magnitude of the velocity of vector C. How are we going to find that? Measure or put a dimension on it, right? Make sure you actually add a dimension. So you want to go to your notes or dimension layer. We are going to add a linear dimension. And from endpoint to endpoint, you're going to add in a dimension showing how long it is. I'm going to move my vector here. I'm going to move this up and I'm going to make it a little bit larger. To make my dimension larger, I need to go to my annotate, dimension style manager, modify. I'm going to make mine a little bit bigger than what it is here. Go to the fit tab and I'm going to put it to 2. That should set as current and close. There we go. Yeah, it's a little bit bigger so we can see it. Remember, when you take a screenshot, you want to make sure they don't have to be the exact same size, but you want to make sure that I can read all of the values, dimensions, and individual items. Okay, what do you think about that?
When I was taking the 6-inch link and I was trying to
So your dimension, I guess my point was, Lars, you have 2.72 what? 235. That is way close enough. That's to the third decimal place. Yeah. So as long as you're, within a reasonable amount here, if you're off by, if you're off by let's say you have 2.8, now I'd be concerned, but you have 2.7235. So you should be okay. Anybody else have that same thing where you're off maybe on the third or fourth decimal, or is it the same as what I have? I don't know. You're off a little bit? Okay. Yeah, so as long as it's within reason, I'm the same. Okay, Garrett. Yep. Okay. So let's look at our answer now. Let's look what we have to answer back. So it says, what is our final answer? So remember, when we drew our vector for velocity of B, we drew it at 3.7174, right? So that means our answer from AutoCAD is 2.7254. So I've got to move the decimal place 2 places to the right? Or multiply this number by 100. Okay, so my answer is going to be 272.5, which is plenty, and that's going to be inches per second. Okay, so if I go back over here, this is going to be my final answer, not what you see in CAD. You need to show the dimension as you dimension it, but your final answer needs to be multiplied by 100. Okay, and because our units here were in inches per second, that means that our units here are going to be inches per second as well. Okay. Now, as far as handing in, as we look at this example, you have everything filled in as we see it here on the handout. But additionally, you will be handing in the original diagram here, a screenshot of this, and a screenshot of your vector diagram with the equation and the dimension for the velocity of C. You might ask, well, how come we didn't dimension the velocity of C relative to B? Because the problem didn't ask us for it. And usually that intermediate link is usually not as, I'm not going to say as important, but it's not something that we're looking for. Remember, input, output. How fast that piston is going. That's the if you would, the function of this mechanism. So we want to, that's what we're focused on. This is just, if you would, an intermediate answer that isn't relative to what they're asking for. So you only have to put what they're asking for. Also, make sure that you have all your labels. Your links have to be labeled. Your joints have to be labeled. Your vectors need to be labeled. And all of your vectors, once you have your vector diagram done, have to have arrowheads, even the C relative to B. Okay? So any questions about this example problem and what you'll be handing in for the practice problems? Okay. If not, then what I'm going to do is I'm going to stop the recording here and we'll take our break.